All right. So welcome you all to the Institute Colloquium. It's my pleasure to invite you and to welcome you. So just to sort of give you a little bit of a background, we were thinking about what to name this series. So I was thinking about whether it's lecture series or colloquium. And so I went back and looked up the Oxford Dictionary, and surprisingly the word has been used, or not surprisingly, the word has been used for many years. Its origin is in the late 16th century, and it actually means to converse. Okay, so it's together, call is together, and loqui is to talk. So therefore, this is the origin of colloquium. So the way we sort of define it is that it's a general talk by the speaker in his or her general area of research and study. And we have taken great care in inviting excellent speakers. So the speakers have been identified based on recommendations by my colleagues. And with that, I invite Professor Sunil Mukhi to introduce today's speaker, Professor Tarun Souradeep.
Hello, everyone. So it's a really great pleasure to introduce Dr. Tarun Souradeep, who I've been fortunate to know for many, many years. It's also a pleasure to see this place full for an occasion which is actually about science. So usually we are doing something or other here, orientation or music or something else. But today it's really science, and I think it's great that we have a colloquium series. And I would encourage all of you to please attend all of them. I should say that I wasn't sure if the hall would be full, but I should have been sure, because every time I have seen Tarun give a talk anywhere, the hall has always been full, whatever its size. We have not been able to test this with sufficiently large halls, but so far he's doing extremely well. And so let me tell you briefly about him. So Tarun actually did a B.Tech in 1988 at IIT Kanpur in mechanical engineering, and he was planning to be an automotive engineer, or to work on automotive engineering. Automobile design engineer to be precise, and he actually spent 6 months or so doing that before he decided to switch to physics. So history will never know whether he would have designed a cosmic microwave automobile. Might have actually been a fantastic discovery, but that's unfortunately lost. Fortunately, he switched to a really interesting and important subject of physics, and his specialization is in cosmic microwave background, gravitational wave astronomy, large-scale structure of the universe, cosmological perturbations from inflation, and generally related topics. He has a very distinguished career, and I think you will get a better picture of it by hearing his talk rather than me listing all his achievements. But some standard things, which are that he's a fellow of several academies, he has several awards and fellowships. One of them I think I would like to mention, the first discovery of the gravitational wave by LIGO in 2015, I think. There was a paper, the discovery paper in Physical Review Letters. Tarun is one of the many co-authors of that paper. And let me also say that, yeah, he has very important scientific leadership roles beyond the science he actually does. He is the spokesperson science for the LIGO India collaboration, which is a very long-term project. And hopefully he'll say a few words about that at some point. And of course, finally, we are extremely proud that since 15 days, he has been a member of IISER Pune, and he is the chair of the physics department here and a professor of physics. So he's in particular a colleague of all of us in IISER, which is even better. So with that much information, I call upon Tarun to give his talk.
Okay, let me begin by thanking the Institute for inviting me for this colloquium, in particular Hari for making it possible to do this soon after I joined. So I got the invitation while I was still in my previous institute, IUCA, which is very close, and many of you would have been there or should go there. It's an Institute for Astronomy and Astrophysics. And to give the talk as a faculty of IISER is a particularly great privilege, and I'm really glad to be here amongst the colleagues, as well as I'm very excited to be here amongst the students. I mean, I've interacted with students from here for a long time, and I really look forward to more of that. So today I'll be talking about the cosmic microwave background and where it is headed, and trying to tell you that there's a lot of very, very active work going on in that area. Although this field has been around for a few decades now, many of you may have heard of my role in which Sunil mentioned in the gravitational wave, which is a new area which is emerging. But to me, cosmic microwave background in the 90s was what gravitational wave is now. And I almost see a very big parallel between how things are developing in the gravitational wave community to how things happened in the cosmic microwave background. So I'll be giving you first a little introduction on cosmology, because not everyone would be aware of that, and then tell you what I wanted to tell you. And so let me begin by asking why cosmology and the cosmic stage. So my only answer to that, whenever people ask me why do you work on cosmology, is go to a quiet place where there's no light pollution, look at the sky. I mean, humanity has been always wondering what's our place here and what is the whole scheme of things in which we are placed. This is, of course, stars in the Milky Way, right? And for centuries, people thought that was it. But if you look away from the plane of the Milky Way, in fact, much further away than shown here, in a so-called dark place in this universe, and look through the strongest telescopes we have, and you would see something like this. So here is a field of many, many, many galaxies. So even a tiny patch in the sky, if you go deep enough, you'll say the universe is full of galaxies. I don't know how many of you are old enough to know of the Cosmic Odyssey book, where it says, wow, it's full of stars, so it's full of galaxies. That's the comment you'll have. And essentially, we are peering so far back, deep into the universe, that we are getting light from galaxies which were emitted when they were just barely forming. So some of these irregular processes are actually galaxies which are just forming, right? So the universe, as far as we can see through these telescopes, is full of galaxies. And this is the cosmic stage. So the full distribution of galaxies, understanding how the structure evolves and how their distribution evolves, is the realm of cosmology I'll be talking about. This is not the only realm of cosmology people talk about. So I wanted to sort of, acclimatize you to the scales involved. So galaxy itself is a massive object, massive in day-to-day experience. So it's 100 to 10 to 100 kiloparsec. Kiloparsec is a unit astronomers love to use, which is about 3.26 light years. So, and so you can imagine light takes, thousands of years to get across one galaxy. That's the size of a galaxy. It has 100 billion stars. Each star has the weight of 10 to the 30 kilograms, in that range. I mean, sun is of that order, and sun is not the largest of the stars, but it's a typical mediocre star. And then you ask, how is the universe around us? So this is a picture of just like an atlas of the universe around you. So here's we at the center. And if you scale out where this is 100 million light years, this stick here, you will start seeing this cloudy structure which is formed of galaxies. So these are galaxy clusters, superclusters. This is very well known Hercules supercluster. Maybe people have heard of Virgo, but Virgo is a relatively neighboring major clusters. Coma are neighboring. But if you go out, you keep seeing this repeatedly, right? And I can keep showing a sequence of zoom, and you will see, this very, very intricate distribution of galaxies. And this is kind of almost like a complete map of what galaxies exist. So these clumps here have, thousands of galaxies in them, right? And this is the network of filaments and nodes at which galaxies have populated the universe, right? This is the cosmos that we are presented with. This is the cosmos we try to understand, right? And you obviously see the rich structure. So if I just cut out a volume out of this sphere, typically looks like this. This is actual data from something called a 2-degree field, and each galaxy is shown with a color which reflects its spectra, but the milky thing is not real, but it sort of highlights the over density. So you can see the galaxy distribution is not a plain regular lattice, neither is it more or less uniform. It has a rich organization. So people who have worked with biological cell plates or cultures or anything, you would see such distributions, and they are not simple. I mean, they just can't so it is a very complex problem that you're faced with, right? How do you understand such a huge universe and it's with such complexity? And that's where I think physicists do well. And I mean, this is not to mean others don't do well, but being a physicist, let me say that one of the things we learn in physics from day, whatever, day zero, in the sense that even before you start your undergraduate in Resnick and Halliday, you always have problems which are idealized, right? Drop friction, drop something. So you always look for a simple model that captures the most essential part of this distribution. So if you were supposed to start cosmology now with all the data, so I'm not giving you a anecdotal historical view of cosmology. I'm giving you a view of cosmology from someone who is granted all this rich data we have now, and say figure it out. As any good physicist would do, you would look for an appropriate simple model. Is there any simplicity that you see in this rich distribution? And one of the simplicities that was observationally seen and theoretically even incorporated much earlier was the fact that if I didn't worry about how far the galaxies were, but I projected them all back onto the sky. This is a picture from the 70s of a Lick observatory survey, okay? And this is the northern cap, this is the southern hemisphere, and there's a part which is cut out. I'm sure many of you will guess why. Any guesses? Yes, the plane of the Milky Way outshines everything. So in those days, we didn't have good infrared, observatories that could peer through the dust, and so that's not there. But if you look at this as a representation of matter distribution, integrated matter distribution in different lines of sight, and if you are blessed like I am with reasonably high-powered glasses, you take them off, and you actually see more or less a smooth distribution. There's no particular region of the sky which seems to cry out and say, oh, I have more galaxies here and I have less galaxies there. Of course, there's some there's some coarseness in the distribution. But if I was to take the first model, okay, it's a very good approximation to say that the distribution of matter around us in the universe is isotropic. Okay, and that's a very powerful statement. Okay, there's something else you have to add to it. One is it is isotropic around me, and secondly, you have to sort of be a bit humble and say we could not be these special guys in the universe for which the universe was spherically symmetrically made around us, and this must be happening for any odd observer in alien civilization in a galaxy far, far away. These two things, once you put these two together, that automatically spills out a cosmological model. And to be honest, and I don't mean people to think that cosmologists don't have very complicated theories, but exactly the standard cosmological model that we work with just comes out of this. The assumption that isotropy around us and isotropy hence around every observer in the universe of matter at distribution at the same time means that the universe has roughly homogeneous distribution of matter. Roughly because we have already seen there's structure in it, but on a grand scale of 300 million light years, it would be true. And that was encoded in something way back in the early 90s as the cosmological principle. That was like theorists saying, let's work with the simplest model and see how far it takes us. And that led to all these Friedman-Robertson-Walker models, which says the Einstein's general relativity, kind of applied to uniform distribution of matter on cosmic scales, leads to a smooth expanding universe. Okay, now you have a simple model, doesn't mean you have a simple life after that. This was radical. In fact, even Einstein shirked from it and said, oh, let me find some way of keeping the universe from expanding, and invented something called a cosmological constant. And the picture is the following. If you believe that the galaxies were dots, and it's a regular lattice here, then at every moment of time, these dots are moving apart, right? And it's not as if there's a center to this. If I were to center this picture, take this dot to the center, I would see the same picture. So it's everywhere galaxies are moving away from each other. And that's the most natural way in which you can explain the first observational evidence for an expanding universe, which was Hubble's law. Hubble found that the further a galaxy was, faster it seemed to be moving away. And moving away was measured in terms of the redshift of spectra, and hence that name redshift. But this velocity is fake. I mean, this velocity can even exceed the speed of light. Okay, so this is Hubble's law. And the other thing is, moment you have a simple model which is actually giving you something interesting, a lot of things come out, tumble out. So if I know the rate at which these dots are separating from each other, which is roughly in the 70, I mean, there is, it's actually very precise in the cosmocracy background, 67.2 with a very small error bar. But, I leave it at this number. You can convert this number to tell you what is the characteristic density of the universe. And that's something very useful for physicists. You work with a system, you should be able to tell me what is the characteristic, densities of gas or liquid or whatever you're dealing with, or neutron star matter, for example. What's the characteristic density? The characteristic density for a cosmologist is some 10 to the 29 grams per cubic centimeter. And that is given to you just by one measurement of how fast the universe is expanding. And to continue this story further, so if you were to take a cosmology course, you would soon feel a bit cheated because you would go through GR, but you will be asked to solve the simplest problem in GR, apply GR to a uniform distribution of matter, and it gives you a model which has only one degree of freedom, which is how fast is the universe expanding in time. So this is the scale factor, relative size of the universe as it grows, and in time. And given that and the matter content of the universe, how much of the matter in the universe clusters under gravity, how much does not. Now this is again, immediately you would notice that cosmology is stepping into an exotic domain. We don't know of matter which does not cluster under gravitation. But yes, there are high energy physicists who tell us scalar fields do give you such situations when they are displaced from their true vacua. And even the vacuum energy of quantum fields would have similar property. And given the different ratios, you will have a different history. And if you are here and you know these two numbers and you know the expansion rate, you can predict what the universe in this simple model will do in the future and has done in the past completely, right? So this model is simple, but it requires you to know the densities of various kind of matter, and in units of that critical density, these are these capital omegas that you see, and end up with an equation which is pretty disappointing. All of cosmological evolution goes into one algebraic equation. They add up all these omegas and it will add up to unity, right? And that's interesting because if you are hunting for different components, then if you have, first of all, you can rule out some. So at this point, we know that the radiation density of the universe is 4 orders of magnitude smaller than anything else. The density of galaxies, for example, energy density of galaxies. Then there are 3 players: the amount of clustering matter, vacuum energy, and the curvature density. Is the universe spatially flat or spherical or hyperbolic? And then as you fix one of them or the other one is constrained to happen, and you might independently measure 2 of them and reconfirm from 2 different angles the same story. And this is what has been happening. The other interesting thing that happens in an expanding universe is if you look at the distribution of galaxies versus distribution of any radiation field. At this time, radiation is much, the energy density is much lesser than that of matter distribution in these galaxies. But if you go to the past, if you take a box and keep shrinking it, the energy density would grow as the cube of the size of the box, right? But matter density, the radiation density has something interesting. It's some density of matter, radiation as if you're in a cavity, microwave cavity, and you're slowly increasing the size, adiabatically increasing the size of the cavity. Then the modes need to fit in the cavity, so the modes get redshifted or going forward in time, and back in time they are blue shifted, and the energy density of radiation actually rises faster back in time than matter. So to add to the simplicity of the whole thing, the early universe is essentially radiation dominated. You don't need to worry about what the matter in galaxies was and all. Early universe, for a large part of the history of the universe, is radiation dominated. And that's important to know. The question is, what do you know about the radiation? And this is where I think there was a very, very critical thing that came in cosmology, and almost revolutionized cosmology from being science where people had various ideas but not checked with data, to a science which has become now very precision science. This is the cosmological background, and this was the serendipitous discovery of the dominant radiation content of the universe. I haven't got the slides to show you that, but this dominates by a factor of 100 over any other background. Okay, and it's a very cold bath of photons at 3 Kelvin, and it wins out in terms of the energy density just by sheer number. So every cubic centimeter of the universe has about 400 such photons, right? And this, of course, got recognized with a Nobel Prize. This is Penzias and Wilson, very, very famous, you must have heard. And we understand it in the expanding universe picture in the following way. In the expanding universe, if I looked at universe back at some point and universe now, this is the spatial part of the universe evolving in time. Of course, I have a two-dimensional toy model here. But you can draw a light cone back. That is the light cone along which any radiation comes. So if I go back, for example, from light from a galaxy, you're always seeing it in the past. It's always on everything lives on the light cone. And as you go further and further away, you are going to earlier and earlier epoch of the universe, which is hotter and denser, right? And as you hit this surface, the typical temperature here is 3,300 Kelvin, and most of the matter in the universe is hydrogen and 25% helium, so roughly 75-25 hydrogen helium. If you take hydrogen helium at those densities and put them at the temperature of 3,300 Kelvin, they are totally ionized. It's a plasma. So the universe prior to this is a plasma. And one of the things about plasma is, because of the free electrons, you cannot really see through the plasma. You can only see the surface of the plasma, right? Similarly, when I'm standing here and looking back along this light cone, I see a wall all around me, which is this plasma screen. And so for an observer, this is the picture one should have. So around every observer in the universe, if you go 14 gigaparsecs away, okay, 14 billion, so about 42 billion light years, then you will hit a wall which is like a plasma screen. So I call it the cosmic super IMAX theater. It's amazing that nature has presented us with an IMAX theater, which is actually a plasma screen, on which what is playing out is the universe as it was 500,000 years old from what is called the Big Bang, the sort of close to the origin of the kind of evolution of the hot Big Bang model that we are seeing, right? And till from 1965 to 1992, this screen was totally blank, right? But it did give you very important information about cosmology. And there's this question of, did the universe have a hot phase? And that comes from the fact that if you look at the distribution, energy distribution of photons in the CMB, cosmic microwave background, and this was measured in 1992 by Kobe Fires from 60 to 600 gigahertz, and you can see that it is extremely well fit by a black body. And if you're not impressed with this picture, I should tell you the error bars here are blown up by a factor of 400 to make them visible to you, right? So it's an amazingly precise measurement that the universe is full of radiation that is completely thermalized. And not only thermalized, it is Planckian, right? Which immediately tells you that by this time in the universe, the medium, the universe must have gone through a phase which was at least 10 million times hotter than it is now. So, we definitely have to live with a hot phase of the universe which is 10 million Kelvin, right? And further, if you want to generate nuclides in neutrons and atoms in, cook them up in the furnace, then you also come up with a universe which is 10 million Kelvin. So that's how the hot Big Bang model seems to go on, right? And as I said, up to 92, this was a blank screen, and that's not very exciting. But people were actively, the field was actively searching. So this is a story very similar to the gravitational waves, where for 40 years people knew that the gravitational waves exist, and only technology kept them from detecting it. It's the same story here. The technology improved to the level where you could detect fluctuations at 10 to the power of minus 5, density, temperature contrasts of 10 to the minus 5. And lo and behold, you saw these fluctuations in the sky from the same satellite mission which gave you this curve. And this is the Kobe DMR. And hence this whole thing got a Nobel Prize in 2006, because these fluctuations were believed to be the seeds from which the rich structure that we see in the distribution of galaxies emerged, right? And that is the story here. So you have fluctuations in the early universe when the universe is only 500,000 years old, which grows through simple Newtonian gravitation instability, even if you don't want to worry about GR, and can give you this rich structure of galaxies. And we actually, as cosmologists, have shown that this is a consistent picture in many, many different ways. The other part which remains, which is what brings me to the cosmic origin, is we do all these inferences based on this perturbed universe in the early times, right? But we don't know as well, equally well, how these perturbations came into being, what kind of caused these perturbations. And we have, however, very good models or a paradigm of inflation within which we work, where such things can arise, right? And this is the story. And a part of that is also, I forgot to tell you, the fact that you saw this uniform screen itself was a problem for standard Big Bang, because you could not explain that causally, because this part of the universe is about 86 billion light years away from that part of the universe. There is no reason for a medium to be homogeneous over such scales. If you draw light cones back from each of them, then they don't intersect, and that was the case. And so you had to have some phase of rapid expansion in the universe, which solved that, but also gave you this origin of structure. And that is what we are out to hunt. And I should tell you why this is such a big challenge to measure it. So it was a 3 Kelvin bath that was measured in 65. The next big breakthrough was to measure these fluctuations, first fluctuations, at the level of 70 microkelvins, right? So 5 orders of magnitude improvement in your apparatuses. And then we have gone ahead, and there's more information. Not only is the cosmic microwave background slightly hotter and colder in different parts of the sky, but it is also polarized, linearly polarized. So if I take a polarized sheet, I will associate a different direction to it. And that's an additional information which you split into something called a E mode, which is the gradient of that soft core headless vector field, and a B mode, which is kind of the curl. And this is for people who are aware of it. But these are very subtle measurements. Again, an order of magnitude more sensitivity is required to get this, and this is still being hunted for. So this is this 3 decades of CMB measurements, started with this Kobe satellite I mentioned in the early 90s. This is when I started my PhD with, so I was lucky that this field came up right then and wrote papers on that. And then there was the decade of the early 2000s. For the first 10 years, there's another satellite which dominated the scene, Wilkinson Microwave Anisotropy Probe. And this decade has belonged to Planck till now. There are a lot of things happening. Just to, so ignore that. Planck sensitivity, just to tell you how big the leap has been, is 1,000 times better than Kobe, and Planck resolution was 100 times better than Kobe, right? And this relentless march is going on. Already Planck is kind of looked as it didn't really have the sensitivity, because they are ground-based experiments which have much finer sensitivities here in this blue curve and in the near future in these curves. Okay. And that is where I want to tell you that all of this did not happen with these 3 missions, but there are many, many ground missions I should acknowledge that gave you a lot of this thing. So what did we achieve from this? We actually achieved, with the cosmological background observations, the first time we had sort called a standard model of cosmology. So I could look into the eye of Saurabh Dubey or this thing, and Sunil here say that, oh, we do have a standard cosmological model, and which is well measured. Okay? And, but not only has that happened, this happened maybe a decade back, we have also established some of the fundamental tenets. We did establish that, what kind of perturbations gave rise to these, the nature of those perturbations, the fact that actually gravitational instability is at work, and all this thing. And these, obviously these major collaborations were highly impactful, right? So we know the paradigm of hot dense universe, isotropy of the universe. This is personally the work that we did at IUCAA with the Planck team. So we were doing some major analysis sections of this isotropy considerations. And also in the perturbed universe, we believe that we have checklisted almost all of the things that an inflationary paradigm tells you should be there for perturbations generated close to the origin of the universe. Okay? We have checked the paradigm of structure formation. We know that it is in fact the growth, and in detailed talks later, maybe if people are interested, I can tell you all of these are stories in themselves. And the paradigm of initial conditions. We know that simplest inflationary model, their predictions are consistent with the kind of universe that we are looking at. And this is this beautiful map of temperature fluctuations, of course, at a much, much lower resolution than what Planck has. And, but this is low resolution temperature in color. And what you see here is this weave pattern, which sort of tells us the polarization field. So we have started mapping out all the information in the microwave background. And this field is on a sphere. This is a full sphere mapped onto, astronomers do that all the time. It's a particular projection. And so we have this polarization field and the temperature field. And for lack of very concrete idea about what should be the field like, one uses the maximum ignorance, right? This is something that we use in. So the maximum ignorance would tell you if this has a particular power spectrum, the best equitable way of distributing all that power is to say that it's a Gaussian random field. Okay, so that's a good guess to begin with. And then you check observationally, is this statistics consistent? And it is Gaussian and random field, and the power fluctuation. So instead of showing you the map, what is important is to tell you how much power is there in the fluctuations at different angular scales. So how much does the delta t values, RMS value look like at degree scales, 10 degree scales, 0.1 degree scale, okay, and so on. And that is encoded in this kind of a wiggly curve called the angular power spectrum. So this goes all the way from the quadrupole, which is spanning almost the scale of the sphere around us, angular scale, to 2500, which means it's pi over 2500, so tens of arc-minute scales. And this angular power spectrum is this predicted from a standard model, is this red curve, and those are actual data with error bars on the top plot. So the error bars have gotten so good that we actually don't really find this useful. We measure things by showing you the differences from this red line. You can see that except for this part, which is very interesting, more or less everywhere the data completely agrees with the standard cosmological model. Okay? The same story for the polarization spectrum, more or less. It's slightly worse than the temperature at this point. It will get better. And the game is, I have these excellent measurements of the angular power spectrum all over the sky. And then these are the green things. This is actual Planck data. And given a choice of how much cold dark matter is there, baryonic matter is there, how fast the universe is expanding, etc., you can predict a curve through physics which is very well known. It's linear physics that's very well known. And then you dial each of these knobs independently, right, and try to find where do I get a combination or where all this matches. And you do that, and it's actually a Markov chain running and trying to find you the minima of this distribution in this multi-parameters. And you see it soon settles down around a thing that matches all the data points. Okay? And this is the success of the cosmological thing. At one go, we have been able to tell you the cosmological parameters extremely well using physics that is extremely well understood. So I want to emphasize one of the reasons cosmic microwave background has been very successful is the physics is linear, and there are not much questions. I mean, they are actually not questions that I have known because I was working on them then. And so more or less everything is settled there. And the physics is beautiful. It's actually the physics of a cosmic drum. So it's like that plasma membrane I told you, plasma screen. And there are perturbations which are perturbing it. And we are just looking at the response function of those perturbations. So one way to do that is to take a piece of that plasma and create a spike in it, which is technically physicists call it the green function, and look at the response. How does a density spike in that distribution do? And you can see that it runs off as a ripple as long as the picture is brown, and then it stagnates as it turns green. That is when the universe turned from being ionized to now becoming neutral. Right? There was this transition I told you when the universe was 1,000 times smaller. And this is where the light comes from. The CMB comes from the spikes and rings. Although it looks like a splotchy pattern, I can actually decompose it into dots with rings around them, and that would be a completely equivalent distribution. What is useful in this is this ring, how big is this ring, is very well understood and calculated. This is exactly 150 megaparsec in the current universe. So at that time, you have to multiply it by the scale factor to get the actual physical distance. But this is cosmologists' way of talking about distances is to tell what that distance would be in the current universe. And we actually see this. So if you thought this was all fairy tale, which people were actually very, would be very right in saying, we actually now see this in the polarization pattern. So this is all the hotspots stacked in the cosmic microwave background of measured by Planck, and you see that there is indeed a hotspot with a ring around it. And in the polarization, it shows you the velocity pattern. And one way to check this is velocity is, remember I told you there's a density spike I put. You can put a negative density spike. And then you would basically reverse the velocity field. So this radial pattern will turn tangential, and the tangential pattern will turn radial, okay, which tells you that the velocity field actually in that plasma has reversed itself around cold spots, which is directly telling you that this basic physics of resonant phenomena on that plasma is correct, right? And we use that. And from there, I'll just give you some examples of why we can get precise numbers out of it, because cosmic microwave background, for example, one of the things it can tell you is the geometry of the spatial hypersurfaces that are evolving in time. And if you look at the angular power spectrum for different universes with different amount of curvature, right? So the green thing out here is the flat universe, and then on this side are universes which are hyperbolic geometry. And if there was spherical geometry sections, then they would have lined up on this side. And we knew that the first peak should be at 220 if the universe is geometrically flat. Okay, we can make that calculation. And that's very simple because you have that 150 megaparsec placed 43 billion light years away. I know the distance of these two triangles, arms of these two triangles, and also this. So I know the triangle length. So I should know that if it is Euclidean geometry, what the angle should be here, angular scale of this peak. And if it is hyperbolic, then it will be less. If it's spherical geometry, it will be more. Similarly, the other thing we can read off extremely well, although you can read off many parameters well, is the baryon density, how much of ordinary matter makes up the universe. So one thing I glossed over is when I made the density spike, what ran out was radiation tightly coupled with baryonic matter. Rest of the matter that clusters, there is matter which is cold dark matter, it does not interact with electromagnetic light. So that doesn't run off like that. And so the height of the, the strength of that ring is completely given by how much of ordinary matter is in the universe, right? And if it is consistent with what we wanted from Big Bang nucleosynthesis, we should have got a 74 microkelvin first peak location and so. And here is data way back in 2006 from WMAP itself, which we actually recomputed here to get the angular power spectrum, and then you fit for the position and amplitude of the first peak, and you find that the first peak is precisely at 220, and the height of the peak is very close to the number you need to explain the baryonic density consistent with Big Bang nucleosynthesis. So it gives you another reason to believe that all the nuclei, hydrogen and helium were cooked in the early universe, not cooked in stars, right? And this is the story. So as I said, it's not only these parameters, but many, many parameters. These 6 parameters are extremely well understood. And it may not be surprising to many people, but when I started in the field in 1990, these were known to factors, right? Some of them were not even known well. And now we know them to percent and sub-percent accuracy, right? And this is the standard cosmological model that is there. So it is simple. Again, I emphasize that we built a very simple model, right? But it's already an exotic universe. There's a lot to contend with. We have 95% of the energy in the universe in forms which we don't know in the lab yet, right? We don't know what the dark matter particles are. We don't know what that vacuum energy, which is accelerating the universe is. Okay, but what is important also, which is some links back to the cosmic origin question, is we did all these inferences. We drew all these inferences from a perturbed universe, a universe which was mildly, perturbed, and we don't know where was the origin, what gave rise to those perturbations in the first place, right? And that must be a clue to the ultra high energy physics that operates. And we have many, many ideas of what the ultra high energy physics should be. And this is an observational window into that ultra high energy physics. We will be able to kind of distinguish between different classes of models. So the best bet we have for the origin of these structures are actually very exotic. They are quantum fluctuations. So it's very amazing to think that everything that we are made up of, the galaxy, the clusters of galaxy, and all the structure in the universe actually arose from quantum fluctuations in the early universe. Okay, during a phase of very rapid expansion, which I told you, inflation, and the calculations are pretty straightforward there in the sense that we are not really heading into quantum gravity there, and we are in a regime where it's quantum fields in curved space-time, and it's believed to be more or less robust, right? So there's no ambiguity about that. So we have a well-calculated paradigm under which we know how these perturbations, and we have this whole story of the cosmological success, matching this universe which was 400,000 years old to a universe which is 14 billion years old now. And then we start asking, what all do we know about the origin of the universe? What kind of fluctuations originate? So for example, we already know that our basic idea of a homogeneous isotropic space is extremely well tested out, because the fact that the cosmic microwave background itself is isotropic at 10⁻⁵, you can put even more serious limits on various deviations through that. Then we know that the geometry of the universe is flat. I told you about this beautiful way of drawing a cosmic triangle and checking whether it's Euclidean or not. And then we also know that the nature of perturbations is nearly scale invariant. We of course see the density perturbations. That's what gives rise to all the galaxy clusters. And we know the nature of this perturbation, and that is that the perturbations have to be of a type where there was no entropy perturbation. And that puts serious limits on the kind of origin models of inflation that work and that do not work. And the underlying statistics of these fluctuations is Gaussian to the extent that we have checked. But there is one thing that is still would be the telltale signature of inflationary universe. That is a cosmic gravitational wave background, okay? And that is supposed to originate right with these perturbations that gave rise to the density perturbations. And that, if you believe in the calculations of the scalar perturbations, okay, the gravitational wave degrees of freedom are identical. They are, massless scalar field excitations, minimally coupled. And if you work through the maths, you know that if you generate scalar perturbations, you generate density perturbations. What is model dependent is the ratio of the gravity wave perturbations to the density perturbations, which we call R. It's a thing you will be talking. You'll hear people talking about going for values of R, and currently we have limited it to 0.07, and this R actually gives you the energy scale of inflation. So once we get the value of R, we will be able to tell you what kind of physics. Is it gut scale physics, or is it lower than that? And we have already an upper limit from this fact that R is 0.07, but that's about it. And this is the to-do and must-do for cosmology now, and cosmology with the cosmic macro background. And that's why this is such an active field. I don't know how many of you followed, there was a few years back a claim of detection of these gravitational waves by experiment on the ground called BICEP. And Planck actually, with its data, showed a few months later that that was erroneous, mistaking dust in our own galaxy for gravitational wave perturbations. And that was a story, and that was also telling you that we need to really work harder with much more sensitive instruments to get to the bottom of this. So this is a plot of that angular power spectrum I showed you. Now it looks very flat because of the many orders of magnitude on this side. This is the temperature one, this is the polarization power spectrum of one kind, this is the polarization power spectrum of the other kind. And already, as I told you, this told you a lot. It gives you the geometry, baryon fraction. This is telling you about neutrino numbers and something called reionization, which I have completely glossed over. But I want you to focus on this green curve. This is what the target is. This is what we really want to get to. And you can see it's orders of magnitude below this, order of magnitude below this at least. So this is the part we have mapped out with our current observations. Planck has been good enough for this, okay? But we need to march on. And there are ground experiments which are getting to some sensitivities here. But the problem from the ground is you don't have access to the full sky, and the ground itself radiates at 300 Kelvin, right? So it's always a big challenge. The atmosphere radiates, and the amazing amount of, so you never get as robust a result as you can get from space. And that is why everywhere, all over the world, people are trying to find out a way to launch the next generation CMB satellite to get these things out. Totally exhaust the information that is there in the cosmic macro background fluctuations, both the temperature fluctuations and the polarization. So we set up in India in 2017 a consortium, and this is since Sunil said that I should mention something about gravity. I may mention something about LIGO India. So LIGO India concept actually started with a consortium. So I'm sort of following that same idea. And we started with something called Indigo Consortium, which proposed the LIGO India project. Similarly, this consortium of Indian cosmologists proposed to ISRO a satellite mission called ECO. And it is supposed to be a complete map of all information in the cosmic macro background that is there to get for doing cosmology, right? And so it has, this is the specs. So you'll get to very low sensitivities compared to Planck, and you'll have some spectral capabilities. But it has amazing scientific promise. One is this gravitational waves of quantum origin. If we see these perturbations, the gravitational wave background, and we say that, yes, inflation happened, that means all the galaxy clusters you're seeing or these things have originated in quantum perturbations, right? So which gives you a big check on this whole, observational test of this quantum field theory in curved spacetime that gave rise to those calculations. So that would be the most direct check of, that. Then this, of course, with every ultra high goal, there's an ultra high risk. Okay, you see it, you don't see it. But there are guaranteed goals if you map out all the polarization information. You get neutrino physics. We can tell you with high precision the number of species of neutrino. And we know that neutrinos are massive, at least uh, two of them are because of the mass gaps that we see. We measure the mass differences, and we will be actually mapping the total mass hierarchy to a level where we will detect the mass of the neutrinos, mass hierarchy of the neutrinos. Okay? And then there's legacy in the sense that very rich, I mean, Planck, half of Planck collaboration papers were on astrophysics. And I didn't spend time on it, but it was mapping the galactic magnetic field. It provided, where all the, cold gases, the factories for molecules, and things like that. And interestingly, quite interesting molecules. I mean, apparently ethanol is very common in many, many galactic clouds, cold galactic clouds. And then, of course, there's always this unexpected discovery that we may do. So we feel that it's a very balanced proposal with path-breaking science, high-value science, and legacy science, and different levels at which we will be actually benefiting the entire community in India with such a mission. This is the map of the CMB fluctuations. Again, the temperature in color, which is at a low angular resolution. But this is the sticks, these are the things, and I told you this is the polarization pattern that I was talking about earlier, linear polarization pattern. And these are the two kinds of modes of this polarization. The cosmic gravitational wave leaves a telltale signature in Worley kind of patterns. See, these are not reflection symmetric. If I take a reflection of a world, it doesn't look the same. But whereas tangential and radial patterns are invariant under mirror symmetry, right? And this is the telltale signature of gravitational waves, and this is what we're looking for. But these are very minute, and we don't see it in the current data at this point, right? And to do that, you basically have to send a satellite, so space, and this is just a schematic. So this is all, the satellite always faces away from the sun, so there's a sunscreen, the hot electronics in this side. So this place is about 300 Kelvin, whereas through a system of mirrors, 3 mirrors, here only we have shown a simplified version of that, the detector plane has bolometers that have to be maintained at 100 millikelvin, so 0.1 Kelvin. And the whole challenge is in the same spacecraft, you have a part which is at 300 Kelvin and 0.1. This has been done, Planck has actually gotten to that. But this has to be, this is a huge challenge if India wants to do it for the first time, or be involved in doing so at this first go. And this whole thing is encased in something that is a solar, kind of shield. And this is how, a mock-up looks. So these are these 3 mirrors, and there's a hole through which, you see the sky, and this is the service module. And this V-groove pattern is to do a temperature separation. And each of this is very basic science and very beautiful engineering. The way you separate out and the fact that V-grooves are better radiators of heat, all this is extremely interesting science. Even although you would put it in the engineering bracket, this is great physics to learn what kind of surfaces they should have and what to do. We will be maxing out the launch capacity of ISRO if we, of course, get selected for this mission. And so GSLV Mark III, which you heard in the news because it launched Chandrayaan, is doing that. It will go to L2, which is 1.5 million kilometers from Earth, away from the sun, okay, and it's a quasi-steady, quasi-stable place, Lagrange point. And it will stay there, look away from the sun, and keep scanning the sky, right, for a few years, okay, and take difference of this thing. And these are kind of the data flow challenges which there. They're very interesting optics challenge, and this all has to be made of silicon carbide, which in India we have just started making them in Leos, for example, in Bangalore, one of the labs of ISRO. So as I said, the big challenge is to have this hot electronics and this thing very, complicated cryogenic chain which separates and cools these detectors down. And the amazing thing is this detector plane. So this has about 14,000 detectors, okay? Each of them is a bolometer that actually can measure attowatts. So there is, and these are not fairy tales. These are being mounted on ground telescopes. So this is an actual image of one such hexagon, right? And so this is again breaking the boundary. For example, when you again talk about LIGO or the gravitational wave detection, we were challenged to be able to measure displacements of 10 to the minus 18 meters, right? 10 to the minus 18 meters. Here, we are being challenged to improve the boundaries of our ability to measure power. Okay, our cell phone is extremely good. I was very amazed to know that the cell phone actually typically can pick up signals if the wattage is 10 to, it's a picowatt kind of signal. So from the tower, so which also I somehow feel should keep you assured for why living next to a tower is not necessarily very bad idea, because the amount of power is in picowatts. It's just that your cell phone and the 4G that is coming was in the lab in the 1990s. So I know the people who developed the labs prototypes of the kind of things that are coming for the enabling the 4G detectors, 4G phones. So you have to push that to 10 to the minus 18. So each of those detectors that you saw can discern attowatt power, right? This is all for experimentalists, square root hertz, RMS power, net equivalent temperature there. And such a project, of course, has many sciences. So we have a very big group. So I just wanted to say it's not just we'll be looking for the cosmic origin and this cosmic background of gravitational waves from its origin. But that is only one of the science goals. There are many science goals that are led out of this. And just like Planck had something like 19 working groups, this will have something like that. And as I said, starting from interesting things which are phenomenal in themselves: cosmic infrared background, cold molecular clouds, dust in the galaxy, the magnetic field in our galaxy. We are able to map it out. These are all pictures of Planck, and we'll do much better with each of them. And I should emphasize there's huge discovery space. I love to use this picture every time. So I was telling you about the universe, and the universe which we think is Big Bang is this, starting from here, a hot phase, which will be kind of 10 to the power 14 giga electron volt temperatures, and then cooling down as it expands to give you this decoupling of matter and radiation, baryons and photons to this cosmic wave background. But what hides here, we don't know, and one of the world's leading experts is out here. We have no idea what is the nature of the space-time from which this universe popped out. We believe it popped out, and there must be something like this everywhere. And who knows that when we map things from the origin, like the cosmic gravitational wave background, we may see hints of non-trivial structures from extremely exotic phenomena that we can see. So I'll stop here. So this is a possible goal of Planck was 2009. We are already 10 years from the launch of Planck, and we are hoping that in another 10 years, maybe we would be able to launch a next generation satellite in international collaboration. This is almost the budgets of this reach a level where it's like CERN, where many countries have to get together to do it. No single country has the resource. And I think if we do that, or we participate in that in a big way, we will be helping ourselves, of course, learning the most fundamental aspects of the cosmic origin, but also getting to use technology and precision science at the maximum, at its limits. Thank you very much.